Hey there, I'm Steve. I want to go over accurate distances on the flat Earth map. Major confusion or point of concern, for example, Australia, is that the actual size, because right now it's apparently looking 2.5 times larger than what we would think it is. For example, how come when we fly over it in an airplane, it looks smaller than how it actually does when we're up in like a weather balloon taking these types of photos? So if you go to, let's say, 2,000 miles up, which might be theoretically possible, you're going to see this photo. But if you physically go to Australia, it's going to shrink down to what the actual size is. Now, why does this happen? I want to go over something called Lorentz-Latitude Hypothesis. Lorentz gave a physical mechanism for what Einstein described as time itself changing. So Einstein claims that as we travel through space, time itself can change. That's not possible. So what Lorentz said is that he gave a physical mechanism for this, and it's mathematically equivalent to general relativity. So this is true, it is accurate, and it acknowledges the ether. So as we're traveling through the ether, the physical world we live in will contract or shrink sizes. This is kind of hard to explain, but it's a well-tested theory. You can look into Lorentz theory. The apparent and the actual sizes are going to be different. The really interesting thing is, though, as you put both objects together, you find out they are the exact same size. It's only our perception of it that is different. So when we're in space, or let's say a high altitude weather balloon, low Earth orbit, you're going to see Australia looking 2.5 times larger than it is. But as we travel through space-time, it contracts to the actual size. Now, that might sound like a bunch of ridiculous stuff, but I believe I am the first person to have accurate distances on the flat Earth map. I don't even think mapping providers will show you this because it completely debunks the globe model. So for example, I just plotted Toronto and China. I checked a globe map to see what it should be, about 11,000 kilometers. Funny though, look at the map they are using for it. They can't even display it properly. They aren't able or even allowed to show a flat Earth map. Google won't, Apple won't, Microsoft won't. But the point is, let's check the distance of this. So this is using the flat Earth model now. I'm going to click Toronto, click on China, and up in the top here we see 11,258. Yeah, it's only a few kilometers off of what the globe model is claiming. But you see here then how we have like a line that makes sense. The globe software should be able to do this. I don't know why they don't want you to see this though. So yeah, see how in the 3D view we can now see the distance traveled, and it perfectly makes sense. Let's do another one just so you know it's not only latitude. Let's, for example, do Australia and New Zealand. So let's go up to our mapping tool, New Z. What comes up? Zealand. Okay, so New Zealand, let's plot a dot there, and then plot a dot for Australia. Australia, I always spell it wrong. I spell it like Austria. Australia. Is this it? Awesome. So we have two new locations now on our map. I want to look at it from this way, just so you can see the really cool map we have, where it even shows like the 60 degrees south Antarctica restricted zone. So this is scientifically and biblically accurate. It's fascinating. But let's check the distance between New Zealand and Australia. New Zealand, Australia. It should be about 4,000 kilometers, and at least they can plot it. Because they use like a Mercator projection. They use some rectangle, which makes no sense because we live on a flat disk, or at worst case, a globe, and you need a 3D sphere. So no matter what, the official mapping platforms are doing something really wrong. But let's check the flat Earth model, see what the flat Earth model predicts for this distance. So let's click on New Zealand, click on Australia, 3,960. Yeah, that's almost the exact same. Now you got to remember, when we choose a location on a large area, where is Australia? There's hundreds of cities we can choose. So even though it's off by 50 kilometers, that's fine. If we could copy and paste these GPS locations into the other model, it would give the exact same value. And then, yeah, we've got a nice little 3D line here. So maps, they don't even let you go into 3D mode, especially a flat Earth 3D mode. Because if you can see this type of model and understand how a Lorentz transformation works, or how the Haversine great circle, for example, this formula here is called the Haversine formula, and it's what the globe model has to do to give an accurate distance for two locations. As you can see, it's lines that have nothing to do with any curve, and it's based on a flat Earth. A lot of people don't know that, and they don't want you to see that. So I think that could be the only reason why mainstream mapping providers refuse or just aren't able. I'm not a genius. If I can code this, Microsoft must be able to. You know what I mean? Like, I'm not the smartest person in the world. So it's not that they're unable to, it's that they're refusing to. And the only reason I can think of is that once you have a 3D and you can start plotting real distances, it becomes extremely obvious that the Earth is flat. I mean, I don't know how else to explain it. Let's try some other distances. What's the distance between like Brazil and Egypt? So Brazil, Egypt, and yeah, let's click it. So let's click on Brazil, click on Egypt. The flat Earth model predicts about 9,700 kilometers. Let's check what the globe model predicts. Yeah, almost the exact same. So yeah, it's only off by like 30 kilometers. And it's really cool. So we have like all these lines now across the map, and we can do like really cool types of measurements. So let's just check China and Egypt. We can click now on China, click on Egypt, and now a new measurement has been done. See that line drawn? So this is the Firmament Tracker's Flat Earth app that we plan to release October 1st. So if what I've shown you interests you, definitely add your email to the sign up list. I'll drop the link in the comments that you guys can stay in touch. This is a scientifically and biblically accurate flat Earth model. So let me clear all the locations, clear all the plotted locations, and let's actually just refresh this. So I want to show you what I mean by scientifically and biblically accurate. So right now I set it to my GPS location, so it detects that I'm in Belize. You can use your GPS and everything. I'm at latitude 17 and latitude 89. But you see how as we move towards the North Pole, Polaris, which is represented by that red dot right there, ends up going straight up. So this models the behavior of our perspective in perfect detail. For example, as we go to the equator, which will have a 0 latitude, you can see Polaris roughly on the horizon. And this is well known. You can use tools like Stellarium, which will give you this view. So Stellarium only allows a first-person view. You can see this. Go into Stellarium right now if you want and turn on what's called the equatorial grid. You'll see this exact view. However, Stellarium and any astronomical software will never let you go out into the 3D view. They don't want you to understand how stuff actually works. So for example, see here how the sun is rising. Where is the actual sun? Not the apparent sun due to my perspective, but where is the actual sun? So on the flat Earth model, we can now see how as the sun passes around us, it's right above us at solar noon, this is what we observe in real life. It's scientifically accurate and from a 3D view, which is just fascinating. You can't find stuff like this that exists. Let me go to December 2024 and let's go to Union Glacier Camp in Antarctica. Is it just called Union Glacier? Okay. Cool. This is cool. So you see now how we passed the restricted zone. So you need a permit to come here and to even test if there is a 24-hour sun, you have to pass that 69 degree parallel, and I'll show you why. Because when the sun, yeah, see right there, for the sun to be visible, you would have to be, yeah, like 58, 59, and this model, I might have drawn it a little bigger than it actually is, but it might be exactly 60 degrees that you'd have to be to see the 24-hour sun as it travels through our perspective. Now, Union Glacier, let me just type it in so there's no debating. I think it's 79, but it might be negative 80. Okay, negative 80. Now, as you see here, what does the flat Earth model predict for a period of 24 hours? Well, it predicts that the sun will be constantly in our perspective the entire time. For example, when the sun is here, when we're facing south, like looking in the complete opposite direction from it, why do we still see it? And that's because of the dome firmament. I don't have it drawn right here because it will mess up with what we're looking at, but the sun is reflecting off the dome firmament, and it's really, really cool how it actually works. A guy named Joe Hanvey kind of modeled this from a physical dome, and it's fascinating. But I think it's important to understand the behavior of the sun as it travels around us. And with this model, as you see, we have lines that we can turn on and off, but I have them on right now because I want to know the difference between where the sun actually is and how my perspective can trick me to making it look like it's setting in the water. It's really, really cool because light bends at about 1 degree for every 69 miles you travel away from it. Yeah, so this is a super cool tool. I look forward to all of you guys getting the app once it's available. So to quickly go over everything again, you want to look into what a Lorentz transformation is. Postulate 1 is 100% true. Postulate 2 is an equation derived by me, and it works. If you want to make your own flat Earth map and measure distances, do it. Please let me know how you're going to do it without claiming that Australia actually is 2.5 times larger than it is. Because we need a mechanism to explain why the scale works. Sure, there's a scale on the Gleason Map. I have a scale right there and it works. But we need a physical mechanism in science to explain that why does it actually contract as we get closer to it. As we travel through latitudes, why is the size of it shrinking? And when we get farther away from it, why does it look bigger than it is? So I think that's very important to understand. The other thing I want to mention as well, this map right here I have for $20 US for sale. You can go to the Flat Earth University store. I'll put a link for that in the comments as well. This is the canvas type. So it's not paper. This is printed on canvas. Super high detail, 60 centimeters across by 90 centimeters high. You can go on Amazon right now, look for this exact same thing. It'll be $35 US. So because we're a university and we're just trying to build trust and get you to know us, this is only $20 US for the exact same product. And it even comes with the hanging stuff. So strongly encourage you to get that. Strongly encourage you to check out our app when it's released. The abilities of it are so fascinating. I'm the lead developer, so I implemented almost everything myself, and it's been like half a year of research, iterating over different models. But we finally got something that works, that is astronomically accurate. And when I say biblically accurate, let me just show you what I mean. So let's go to my location in Belize. You know how the sun can appear to rise or set from the water, and that Enoch seems to describe portals and gates that the sun seems to rise out of? So we support the Enoch framework. You can go into your first person view, see what it looks like. Now, what Stellarium and mainstream astronomy software will do is they will draw your perspective larger than it actually is. So this is arbitrary. We don't actually know the position where the sun's setting because you would need to be in a 3D view to see that. From our perspective, it disappears behind the skyline, the trees. We will never actually be able to see a 0 degree unless you're in an airplane. And when you are up in an airplane, there's photos of people who see the sun rising and setting from the water. So what I'm saying is true, and I wanted to make sure we modeled that because everything needs to be able to be described and accurately modeled. Let's go back to September 7th, make sure my location is set. And let me just zoom up on this part right here. So you see the sun, how it's at 62 degrees from my horizon. Let's go closer to like a sunrise around like 7 or 6. See how it's like 16 degrees and it goes from like 0 up. So this model is astronomically correct. You can go outside, even go into your first person view and see, okay, where is the sun supposed to be and what orbit is it following? So that's really important. These lines that I'm drawing are not random. They're curved for a reason because that's how the sun travels over us on our flat Earth. So if you're not familiar with the path the sun takes, it actually change where you are in the world. So let me put my celestial sphere up to like somewhere in Canada. So I have friends who will mention that, see how the sun goes around that loop? So let's see, I'm just trying to think the best way to view this. See that curve? It goes like there and comes all the way out and down. And then from the first person perspective, you see that? So that curve now that we're up in Canada, is completely different than my curve in Belize. Let me see if I can click the GPS and automatically move us. Yeah, I just did. See now how for me, my perspective shows the orbit completely different. And this is accurate. For example, when you go to the South Pole perspective, because now we're looking at the bottom of the firmament, this blue dot is where, for example, the Southern Cross will start to rotate around, and those celestial bodies rotate around there until when we're at like Antarctica and we're looking straight up to see the Southern Cross. So this is fascinating. I just wanted to show you guys that distances are accurate on our app, so you can use this as a real mapping platform, real navigation, and do real research. You can plot coordinates, draw lines between it, do calculations, and we're still adding features every single day. So I just got excited about this one here, so I wanted to make a video and show you all. Have a wonderful day.